So let's get it started. We are moving forward to a new topic, changing gears, and we're going to be talking. We're going to spend quite a few time talking about functional spaces, convolutions, and other types of operations, mathematical operations that are very useful for filtering, specifically linear filters and the like, low pass filters, mid pass filters, high pass, meaning high frequencies, low frequencies, spatial frequencies, and so on. But before we probably go into the details to define all these terms very formally, right, and spend some time explaining all the math behind us, let's define things a little loosely, right? Still mathematically, but still a little loosely, and then we'll define things more accurately, and that will allow us to do even cooler things than the ones that we have been doing. Okay, and that will be the second to last topic that we cover in this class. The last topic is going to be color vision. Okay. All right. So one of the ideas behind linear filters is to represent the image, or to rewrite, if you will, the image as a linear combination of its own terms, right, of its pixels. So let's see how we can do that, and then let's see why this is important. So as always, I'm going to start with an image of p pixels. And remember, an image is nothing else than is a matrix, right? A set of rows and columns. So many columns here, many rows, and all the way to the last few rows here, right? And what I'm going to do is I'm going to take a specific region of that. So I'm going to take a specific window, let's say, of that, like this, right? As we have done before. And let me rewrite this here. That's going to give me, say, the center column and the center row of the window. So this is the pixel at the very center of this window that is selected here, right? And let's say that I'm going to say I have here k columns, or and here on the other side I have another number of columns, say k again, right? So this is the mid column, and since this is a square window, we're going to assume that the number of rows here is also k. So I now have k here, k rows, and k rows here. Okay. So far so good? You all with me? Okay. So let's call this center pixel. So let's say that this is my image. Let's call that image F. And the center pixel is going to be given by some value ij, specifying the row and column, or column and row of the image. Now this window is, what's the size of this window that I have defined here? Anyone? 2k plus 1, very good, times 2k plus 1, very good. So this is 2k plus 1 by 2k plus 1 pixels. And now what I can do, I can rewrite my original image as a linear combination of these windows. So I can sum over all the u's, and I can sum over all the v's of all the f UVs that I have here. Now U in my case is going to go from, say, if this is Rj, this is going to be I minus k and I plus k, and V is going to go from j minus k to j plus k, and I need to normalize this, right, for all the summing terms that I have. And how many summing terms do I have here? I have 2k plus 1 here, 2k plus 1 here, so this is 2k plus 1 squared. You can also rewrite this, obviously, if you prefer, as you can take this term out, 2k plus 1 squared, then the sum over all u over all v of f uv, right? So when I do this, what happens? What happens is, note that what I'm doing here, I am equaling this pixel in this new image, right? There's going to be a new image if I consider all the possible rows and columns of my image, right? I'm going to create a new image that is equal to the pixels in the original image, right? Multiplied by some weight vector, right? So this is a weight that is multiplied by each of the pixels. So this is end up being a linear combination of the original pixels, right? Now, in this simple equation that I have given here, the weights are the same for every pixel, right? So every pixel is equally weighted. But I could come up with many other possible weights. So for example, I could give a weight of 1 at the very center here, right? And a weight of 0 for all the other pixels, right? What would that do? What would then R be equal to when I generate this new image? So with this equation, I can go from F to R, right? So from my original image F to a new image of the same size R. And what's this R going to be if I set this equal to 1 and 0 everywhere else? It's going to be exactly the same, right? I'm not going to do anything. Now, if I change this, and the weights are always, when I sum over all the weights, are always sum up to 1, right? So if I call these weights, let's call them Wij's, right? So when I sum over all the Wij's, these are equal to 1. And I have this equation here, right, where each pixel has the exact same weight. Then what's this going to be equal to compared to this? What's that? Blurred. It's blurred, correct. And why? What's going to happen? So each pixel here is going to represent what exactly? The average of the pixel values, right? The luminance of the pixels in a specific window, right? So you could change that that weight function to do whatever you need it to do, and that's what we're going to do here. Now, a couple of things before we do that. Note that these filters, right? This is called a filter, by the way. This is called a linear filter, right? Note that this filtering that we're doing here does not depend on where the filter is located. And hence, we will say that this linear filter is shift invariant. Right? Because if the filter doesn't change, doesn't matter where I locate this. And the reason we call it linear filters is because they define a linear operation. If I apply this equation here to two images, right? So I have F1 and F2, and that gives me two outputs, R1 and R2. And now I sum R1 plus R2. That's the same than applying the filter to F1 plus F2. Right? And therefore, that's a linear function, right? Okay. Now, this also defines what's called an image convolution. What I'm going to do, let's define these weights. I say Wij. In your book, you have them called Hij. That's in the book. Doesn't matter, right? Same thing. So I'm going to rewrite this with this new notation. So this is sum over all u, sum over all v, right? U goes from I minus k to I plus k, v j minus k, j plus k. And Wij, actually, this is incorrect. I can be right. That should be, let's think about this. That should be W, which is the weight, right, of where I'm at. So if I start at I minus k, that means that I start at this location and at this location. So I start right here, right? So that is going to be represented by W I minus u, right? And j minus v, am I right? Times my image at the pixel uv. And that is called a convolution. And you could say capital W, right? It's the matrix of the weights. Convolution, which we usually write as this asterisk, right? This is a convolution with my image, right? And this is known as a convolution. W here, or H, is called the kernel of that filter that defines this convolution. And we will typically say that an image F has been convolved with a filter or a kernel W. So let's see why we even care about this, right? Why did I actually define this? Let's get back to that case where all the weights are the same, right? And let's assume that I make this window really small, right? Maybe 2 or 3 pixels on each side. That may allow me to eliminate noise in the image. If I take an image and there are just very sparse noise points, right? That used to be more common when cameras were analog, right, rather than digital. In digital, you can have it because not all the pixels in the CD camera work perfectly well. In fact, if you have a really good camera, if you have an SLR that is maybe 14, 16 megapixels, take a few good images with good lighting, right? And then import it in the computer in some program like Photoshop, and then zoom in as much as you can, and without going to the pixel, right? And you will see that there are pixels that have noise, right? That are incorrect. And you don't see it when you print or when you visualize the image because there's so many pixels that everything gets smoothed out either by the screen itself or by your visual system. But if you zoom in, you'll actually see that. And the way to resolve this is by applying this filter, right? It's just a very simple filter where you either have a small window, or if you have a large window, you only consider the pixels at the center to have some value, right? Such as that all the values, all the weights add up to 1, and all the others in the surrounding area equal to 0, right? And that by averaging about each of the pixels, what you are accomplishing is by you smooth, right? You compute the average, so you smooth the image locally. And if you have 1 pixel that is defective, then you smooth it out, right? You eliminate that information. Now, of course, the problem with this is that if the window that you select, right, or this region that you select in the window is too small, then the smoothing is so little that does not allow you, or does not accomplish the goal of smoothing out the noise out of the image. On the other hand, if I make the window too large, then I end up with a blurred image, right? So finding a compromise is not always an easy thing, but you can do it at least manually. It can be done until it's pleasing to your eyes. An extension of this, which is actually much more typical to smooth out the noise, is to use what's called a Gaussian kernel. And what that means is that we're going to use a Gaussian, a kernel that looks like a picture of a Gaussian, right? So remember, a Gaussian, univariate Gaussian looks like this. Now in 2D, it will look, this is in 1D, right? In 2D, it'll look something like that, right? So like a mountain. And then these are my 2 dimensions here, right? This plane defines my 2 dimensions, and this defines the density of the Gaussian. So if I look from above, right, I took a picture, say, from above, and I assign higher weights, right, obviously, to that point than to points that are on this side of the curve, then I would get something of that form, right, where the intensity values on this area are less than the ones inside, they're less than the ones inside it, they're less than here, and you'll see this mountain, right, in luminance. So that is a Gaussian filter, and obviously my Gaussian filter can be defined as the function where G sigma, where sigma is defines the variance of the Gaussian of xy. It's equal to 1 over 2 pi sigma square times the exponential function of negative x squared plus y squared over 2 sigma squared. Right? And for those that know this, if you don't know this, don't worry too much. You'll learn it soon enough in other courses. This is an exponential function that defines the density, right? And this is called the normalizing constant. And don't write this down. Either you know it or you don't. It doesn't matter. And the reason for this normalizing constant is because you want this density that you are defining with this function to be equal to 1, right? So this function f, this is a function f. When I integrate this function over my space, then I want, well, over my whole space from negative infinity to infinity, basically, I want this to be equal to 1, right? And that's what that normalizing constant guarantees me, that this integration, which is nothing else than what I had here. Where do I have this here? Of course, this is in the discrete, in image is discrete, so I convert an integration to a summation term, but in the continuous, I integrate, and that has to be equal to 1. Now, you have in the slides that are on Canvas, you have examples of an image that has been convolved with a Gaussian kernel, right? With different variances. So the larger the variance, the more pixels that you average into the equation, right? And with that, you can see how this works. Okay, so far so good. You're all with me? Now comes the really cool stuff. So this is very easy, right? I mean, you just compute an average. You can eliminate noise. Not very useful these days. Cameras are not noise-free, but you know, the amount of noise that you get, it's not really high. So not very useful. But what else can we do with these kernels, with these filters? Let's see. It's interesting. One thing that we can do with this is to detect changes of the shading of our object that's represented in the image, or objects that are represented in the image, right? Let's see what that means. So detecting shading changes. This is really cool. For example, let's just for sake of discussion, let's say that we want to define a kernel that allows us to detect positive intensities, meaning high values of intensities, on one side of the kernel, right? Versus negative, meaning low intensities, right? Low intensities on the other side of the kernel. How we go about doing that? Say that we have, for simplicity, a kernel that's 3 by 3. Here's a possible kernel. I don't care about the first row or the last row. And what I want, I don't care about the center point, but I care about changes that go from positive to negative or negative to positive. You just change the sign, right? A filter like this would respond to changes in brightness, right, in intensity or luminance, about the horizontal axis only, right? I could define another kernel, say W prime, which does the opposite. Instead of detecting horizontal changes, it detects vertical changes, right? Something like this. See that? That's pretty interesting. See that? So let's see what we mean by this, because this is something really cool that we'll be taking advantage of. Let's go back to shading or luminance changes in an image. Now, for now, I'm going to convert an image into just 1D for simplicity, right? As per usual. Okay. So imagine that I have something like this. I have a one-dimensional image, right? This is my dimension here. And let's say that this pixel here, these first few pixels, have an intensity of, so this is the pixel, and this is the brightness or luminance. Okay. So it has a value here, and then all of a sudden it changes to a lower value, right? And I want to call this positive and this negative, right? The positive and the negative side. See that? Okay. Or I could also have the opposite, I guess. I could start the negative side and then go to the positive side. Now, what do I want? What I want is I want to find a kernel that I convolve with this image, right? A kernel that I convolve with this image and gives me a result that detects that I'm going from an area of high luminance to an area of low luminance, or from an area of low luminance to an area of high luminance. Right? Now, remember that we talked about this when we were talking about optical flow and template matching. Do you remember this? Remember optical flow? What did I call this? For optical flow, when objects move. All right. What's that? No. All right. Let's go back to this. We'll come back to it. We'll see. We'll see what that was. So I'm going to convolve my filter with this, and let's say that I want this filter to be, I don't know, let's say larger than 0, and this negative smaller than 0, right? Or vice versa, meaning that I know that I'm going from positive to negative, and that I'm going from negative to positive. All right, so how am I going to do that? Let's think about this. If I use the Gaussian filter, right, the Gaussian kernel that I defined before, okay? This is the one-dimensional Gaussian kernel because I have one-dimensional images now, right? G sigma. So if I have this, and I assign this to H, right? This is my H. And I convolve this image with this H. What am I going to get? What's going to be my result? Maybe something like this, right? It's going to be smoothed, right? So going to allow me to detect a change. So, and in that other case, right, here, I'm going to get this, right? Is that going to allow me to detect changes? No, all this is doing is it's telling me that it's smoothing out the original image, right? But that's not detecting the change. How about if I now compute the partial derivative of the Gaussian kernel with respect to my variable x, all right? Let's say that this is x here, right? Then what is the partial derivative with respect to x of the Gaussian kernel? So again, if this is my Gaussian, the first derivative, right, of the Gaussian is going to look something, let's say the gradient increases here, right? Right? So it's going to look something like this up to this point, right? So maybe I can do a better job. Huh? It's going to look something like this, right? Okay, still not good. That's a little better. How about this, right? Now, what's the gradient at this point? Okay, so this is going to go all the way down. And now I'm going to decrease, right? Right, so it's going to be something like that. So that is the, oh, it's right here, the partial derivative. Okay, now let's think, what will happen if I take this h and I go back to here and I apply this new filter in this new kernel to this image? What am I going to get? Let's see. I have no idea. Do you? We need to check, right? So what I'm going to do, I'm going to place that kernel, say, here in this position. Okay? You see that? And I'm going to do a convolution, right? Which is meaning that sum of all the pixels. So a convolution is nothing else than adding all the pixels, right? Multiply this function by this function at each pixel. You agree? So if I multiply all these values by this value, it's going to be a total number of, say, alpha. And if I multiply this part by the same value, it's going to be equal to what? Negative alpha. So alpha plus negative alpha is 0. So this is going to be 0, right? Now, at one point, this function is going to be right here. Now here, I'm going to add alpha. And here, whoops, what's happening? So all of a sudden, I'm going to get here at this point, I'm going to get a value, right? And if I shift this a little to the left, right, then what I get is something like this. I get some subtraction, but not all, right? And this is exponential because it's an exponential function. So it's going to look something like this, and then something like that, right? Now, the thinner that that function is, meaning the smaller sigma is, right, the closer this is going to be to just 1 point, right? And all of a sudden, I have a value, a function, that is telling me that at that point, you see at that center point here, I'm moving from an area of high intensity to low. Isn't that pretty cool? It's incredible. What happened here? If I do the same, but now on this other one, I wonder. So if I have my function here, then I subtract alpha, I add alpha, so again, 0, right? So it's going to be 0 up to this point, right? And at this point, it's going to happen the same thing I had before, right? But, oh, wait a minute. Now what's happening here? Now I add a negative, right? Right? So now I'm going to have something like this. Is that right? So I have a positive result and a negative result that tells me that I'm going from high luminance to low luminance, or from low luminance to high luminance. That's pretty incredible. This is the power of linear filters. They can tell you a lot of things. They're very useful, right, for the algorithms that we have derived. For example, going back to optical flow, if two regions belong to two different objects, we call them motion discontinuities, right? Because these two objects move in different directions, assuming that the two objects move in different directions. If we have an algorithm to detect where these potential motion discontinuities are, we can address that problem, right? That's pretty cool. This has another application, or what I just said has a specific application. Anyone can think of a clear application of this that we just derived here? Edge detection, excellent, yes. So this can be used to detect edges. So if I have objects, right? Have an object here, and maybe you have another object here that have different luminance, right? So this has luminance, say 1, and this has luminance 2. Then I can apply this algorithm, and it's going to detect just the edges, right? This is just going to be the output. It's going to be a little blurred, so it's going to be, the edge is going to be detected, obviously, like this, a little thicker, right? Because you're going to have this nice Gaussian function here, exponential function, that's going to define the edge. Now, obviously, that's not that simple yet, because here I'm only in 1D. What I just did is a leap of faith in saying that it can be applied to 2D. Well, but it's not that complicated. Let's think about this. If I compute the partial derivative of my Gaussian filter with respect to x, right, then I'm finding edges in the x direction. But I could do the same by computing the partial derivative with respect to y, and that's going to give me the edges on the y direction, right? And you know what? I can also compute the partial derivative with respect to x and y, and so on. Y and x, whatever filter or whatever type of edge I want to detect. Now, the second derivative in particular is a very common solution or kernel that is used to detect filters. That's called the Laplacian. So let's define it. The Laplacian, we're going to define it as the second derivative of our function, xy, which is going to be equal to the second derivative of x plus the second derivative of y. And that is a very common way to detect edges in the x and y direction. where f typically, not always, but typically is the Gaussian function, right? And then you can detect the edges or the zeros. Sometimes they're called the zero crossings because the function crosses 0 at that point, right? The zero crossings of the gradient of, say, the Gaussian convolved with our image. Okay. How are we doing? So far, so good? All right. So what I want to do next is I want to take a detour from this, now that we know what we want, right? And at least one of the things that we want to accomplish, and extend our knowledge of the math that we have learned in other courses to the math that are going to allow us to do this and even cooler things, like the trifocal tensor. Do you remember the trifocal tensor I mentioned back when we were talking about epipolar geometry? These new math are going to allow us to solve all these different problems, right? And they're nothing different than the math that you're familiar with, than the math that we have worked with until now. You just need to get used to the new terminology, but there's nothing new, okay? Or nothing fundamentally novel, right? But we'll take it one step at a time, and stop me if you have questions, because the math that you know, you still don't know it, but the math that you already know is extremely powerful, only if you extend it a little bit, okay? And that's what I want to do, give you that little extension. So what I'm going to do for the next 2-3 lectures, hopefully just a couple of lectures, we'll see. I want to introduce you to Hilbert Spaces. Okay? Let's see what this is. Now, Hilbert was a famous mathematician. I mean, famous mathematician is a way of saying it's an understatement. He was the mathematician of the time. I mean, so much so that when Einstein was working on his theory of general relativity, he faced a mathematical problem he couldn't solve. He couldn't solve himself. So he went to talk to Hilbert. And Hilbert thought about it, gave him some pointers, and then finally came up with a solution. Einstein then claimed that he came out with the solution by himself, a few weeks later, but I mean, who knows? But he was the mathematician to talk to. Hilbert also thought incorrectly that all mathematical problems had a solution. Right? So he wrote a famous book of the 100, or I forget the exact number, I think it was 100, the 100 most important open mathematical problems, right? And his point was, I don't know how long is it going to take us to solve these problems, these mathematical problems, but we're eventually going to get there, right? And here are the ones that I think are the most important ones, and I challenge people mathematicians to solve them. Then Kettle, years later, published a famous theorem which basically destroyed the whole idea that all mathematical problems are solvable. And basically, I mean, the basic idea of Kettle's theorem, famous theorem in his PhD thesis, was that he defined a theorem that if you could, it's a contradiction. If I can prove the theorem, then math is wrong, or the theorem is wrong, right? It's very simple. It's a very simplistic way of describing his theorem. But basically, if I am able to prove this, then everything that I have stated is absolutely wrong, which means that you reach a contradiction, right? But the importance of Kettle is that he proved that not all mathematical problems are solvable, right? So Hilbert, and then Kettle, and then, of course, Turing led us to the importance of the stopping, the algorithms that have a solution or not that will stop in a finite amount of computations or time. So all this is very interesting stuff that it's covered in a variety of courses, and if you're interested in extending your grad studies, those are things I recommend that at least you get familiar with, and they're very good books that are very easy to read. You don't need much mathematical knowledge to read them. That will summarize this for you. I'm happy to point them to those books if you're interested. Okay, so up to today, we have defined almost every object, and by object I mean, for example, an image, right, as a vector in some vector space, correct? That's how we've defined our images or our objects. Let us see in detail what that really means. Let's imagine that I start with a vector x, and x is defined in some vector space. Let's say, let's make it real simple. Let's say that I'm in the Euclidean space, okay? Remember that early in the course we started there too. We defined the Euclidean space of 3 dimensions, for example, right? So x was equal to, say, x1, x2, x3, and this is defined, say, in the Euclidean space of 3 dimensions, right? And we saw that this is not really true, right? This notation is not complete, right? Does not tell the whole story. Remember that? There's something missing in that notation. What's missing from that notation? What's that? The basis vectors, right? So I'm missing here the basis vectors that define my space. So there's a vector E, E1, E2, E3, that specify the basis vectors of the Euclidean space of 3 dimensions, right? So in fact, this is not the correct representation. The correct or the complete representation should be x1 times e1 plus x2 times e2 plus x3 times e3, right? That is the correct representation. And what that means nothing else than if I have a 3-dimensional space here, right? I have, in the Euclidean space, I have e1, e2, E3, the basis vectors that define that space. These EIs are of norm 1, right, in the Euclidean space. And EI transpose EJ, that means the inner product is equal to 0 if I is different than J, and 1 if I is equal to J, right? Because that defines the norm, right? And that's because they're all orthogonal to one another, right? Orthonormal basis vectors in this case. Okay, everyone still with me? So, more generally, we're going to define a vector space, right? A vector space like this. This is a vector space because defined by these basis vectors, right? We define a vector space as a set of vectors I'm going to write set of X, right? By this, I mean this is a set, right, of my vectors X that obey the following two rules. Okay. First, scaling, also called vector scaling, is defined and closed. And two, addition is also defined and closed. Now, by closed, what we mean is that when I do one of these two operations with elements of my set, I end up with another element of that set. Right? Now, remember that we spent quite some time defining affine spaces and affine transformations, right? And that followed that, or this definition that's given here of vector space, right? My affine space. Remember when we defined the vectors and we could multiply them by a scaling factor, we could do addition with them, right? That's an example of a vector space that we have already derived. Okay, so far so good. Can I move on? Now, what's special about vectors? Anyone can tell me what's special about vectors? How about nothing? Right? Can I apply this to a matrix? Of course I can, right? What's wrong with matrices? So the same concepts that are applicable to vectors also apply to matrices. And what's an image? It's a matrix, right? So why don't we look into matrices? All right. So for matrices, we have, let's see, addition, for example, A plus B, where A and B are two different matrices, right? And I need to follow these two rules. I started with a second one of addition. Okay, my bad. So for addition, that has to be defined and closed. And addition for matrices, I can define them as Aij, meaning that Aij is the ith j entry, right? The ith row, jth column of my matrix, plus Bij, right? And so that was 2. And how about the scaling? A scaling is multiplying by a scalar. Alpha times A is going to be equal to alpha Aij, for example, right? So there's nothing special about a vector. everything that we know about vectors applies to matrices. For example, you know how to compute the average, the mean of a set of vectors, right? If I have n vectors, I can compute the mean, right? The average. Well, I can do that for matrices as well, right? So the mean is going to be equal to, let's call it A bar, my mean, is going to be equal to what? Going to be equal to the sum, right, of I from, say, 1 through n of A sub k, can I call them like this, right? If I have where AIs are my matrices. Okay, and now I need to multiply this by 1 over n, right, to compute the mean. True? Well, same thing, right? So that mean uses the two properties of a vector space, but now for matrices, right, which is the addition and the scaling. You see that? Another thing that we have used and that you're very familiar with is norms. What's a norm for vectors? Let's remind ourselves what the norm is. A norm is nothing else than a function, right? A norm is a function that satisfies a number of properties, right? 4 properties. What are those? Anyone can tell me? So a norm of a vector x, for example, I can usually write it as this, right? That's what we usually write it with. And it satisfies 4 properties. What are those? What's that? Non-negativity. Very good. So the norm of x has to be larger or equal than 0, right? That's non-negative. What else? What's that?
X plus y, the norm of x.
Oh, the triangle inequality? Very good. Let's do the other ones. Let's do the easy ones first. That's the last one. Yeah. Yeah, but I agree. Very good. What else? How about the norm of x, it's equal to 0 if and only if what? The origin or the 0 vector. Very good. Right? It's all zeros. Very good. One more. Let me give you a hint. This functional mapping, right, the function that computes the norm, is linear, which means what? Which means that if I multiply x by a scalar lambda, that's equal to, what's that? Yeah, say it again. Close. Anyone else? Very close. Alpha times? Okay, very close. Almost. We're almost there. So this is what you're saying, right? That's not actually correct. What am I missing? Yes, the absolute value of alpha, right? Very good. Okay. So this is the scaling. The second one is the nullness, right? Call this the nullness. This is the scaling property. And then there was the last one, the triangle inequality that was mentioned, that if I have x plus y, right, the norm of that has to be smaller or equal than x plus the norm of x, excuse me, plus the norm of y. And that's a triangle inequality. Okay. So there's scaling but not addition, so it's not a true linear function. So as I keep saying, this is, of course, a functional mapping, right? So I have a function f, right? F given by this, right? So this is my function f, right? I can write f of x instead of these bars within around x, right? Same thing. So f maps from a vector of p dimensions into a real number, right? It's functional mapping. Now, can we apply these to matrices? What do you think? Why not? Right? Is there something special about vectors? So how about matrices? Well, for matrices, I need an f that maps from, say, m by n dimensions onto R, right? That's the only difference, but it's still a functional mapping. And let's see, for matrices, I want the same thing. I want for a matrix A, a matrix of m by n, obviously. I want this to be larger or equal than 0. Right? I want f of a to be equal to 0 if and only if A, it's a matrix of all zeros, right? I want the scaling property. So I have absolute value of alpha times f of a. And the triangle inequality, so f of a plus b, smaller or equal than, f of a plus f of b. Okay. So let's see a few examples. So for vectors here, I could compute, for example, the 2 norm, right? The 2 norm of x. Say usually you'll see written with a 2 here, specifying this is a 2 norm. Now let me probably do the square of the 2 norm. This is, anyone? What's this equal to? X transpose x, right? The inner product, right? Excellent. And so on, right? You could compute the 1 norm. What's a 1 norm? The absolute value, right? Instead of the square. And so on. You can compute the p norm in general, which is every element of x to the power of p, and then or the whole result 1 over p, right? Okay. So we can do the same thing. So you know the norms here. We can do the same thing here, right? So there is a very famous norm for matrices. It's called the Frobenius norm. Which is equal to, so I'm going to write the norm of A. Now I'm going to write F here instead of the number 2 or 1 or what have you, to specify this is a Frobenius norm. This is equal to the sum of I from 1 through n. I said this is m by n, so m rather than n, and the sum of j from 1 to n of aij. Now I'm going to square those. And this, I'm going to take the square root. Okay? See that? That's called the Frobenius norm. Now, does this look familiar to you? What does this remind you of? True, but what else does it remind you of? Does it remind you of a norm here? Let's see, what's this equal to? See what this is equal to. This would be equal to the sum over I, right? The sum, so this would be xi, right? Square and square root. Is that right? Does it look familiar? A little similar, right? But this is the true norm. Be careful, this is not the true norm for matrices. This is Frobenius norm. Okay? Why not? Well, to find the value of the true norm, what we really need to see, to know, is what is the length of a vector, right? Of a vector x here, projected onto another vector, say z, right? A dimension that maximizes its value, right? But this z vector has to be a basis vector, so z has to have norm 1. So the same applies to matrices. So I can write for the true norm for matrices, I could write that a z, where again z has norm 1, right? So what I want to do, I want to find the projection, right, for the true norm. And this is a functional mapping of my a, right? Or let's say functional mapping, a function of x that does ax, the true norm, but with the constraint that x has to be norm 1. So I'm going to divide by x, the length of x. And what's this equal to? Let's do this operation in here. This is ax times ax, right? Or I'm going to transpose, ax transpose ax, ax transpose ax, right? Or I'm going to write this as x transpose h transpose ax divided by the norm, the true norm of x, which is also x transpose x, obviously. And does this look familiar, this equation? This is the least square solution, right? Right? So the true norm of a matrix is actually an eigenvalue decomposition problem. So we want to minimize this, right? So if I have my z here, f of z, this is going to be equal to some lambda square, right? Some value. And I want to find the minimum value of this. So to do that, I'm going to solve for the eigenvalue decomposition A transpose A z lambda square z, right? And therefore, this is the eigenvalue of A transpose A, right? So fascinating. The 2 norm is the eigenvalue of A transpose A, the 2 norm of A.
Why do you want to minimize?
You want to find the projection of A onto a dimension, right, that defines your norm. And that other equation that I have there is a Frobenius norm, which is very typically used because that simulates the linear least squares, was a point made earlier, that we usually associate to the 2 norm for vectors, right? So when we work with matrices, we like to work with the Frobenius norm rather than the 2 norm, which involved an eigenvalue decomposition problem. Now, there are many other norms, obviously. So the P norm in general, this was a 2 norm. The P norm in general is going to be defined as the maximum. I'm going to write it this way, which means in math what this means is that the maximum may actually not exist, right? I mean, it just go on forever. But this just means nothing else. And the maximum of x different than 0 of ax p divided by xp. Okay. There are some equalities that are probably useful to know. So if you compute the Frobenius norm of a matrix, we know that this has to be larger or equal than the 2 norm. And this is actually smaller or equal, the Frobenius norm, than the square root of n times the 2 norm of A. And obviously, the particular cases of for p equal to 1 and infinite. For 1, this is the maximum of from j, say 1 through, what was it, n. The sum of j from 1 to I. Okay, which is which? Right, this should be I, right? From 1 to m of aij. And the infinite norm is the maximum of I from 1 through m and j from 1 through n now of aij. Okay. All right, any questions? All right, let's leave it here. I'm going to move to inner product next, and then that's going to allow us to give a almost correct definition of a Hilbert space, and then that will allow us to define tensors, which is our next big topic. All right, I'll see you next week.